Okay, so let's come back to class. So basically, we have finished the sequence alignment problem, and we are actually starting to talk about the shortest path problem. So this is actually a problem that we are familiar with, especially when we introduce Gradius algorithm and Dijkstra's algorithm for the shortest path problem. But therein, we can only study a graph with non-negative weights. So here we notice that if a graph has negative weights, actually Dijkstra's algorithm is going to fail. And some like a naive fix on this, for instance, maybe you want to add like a positive constant to every edge. So this is actually going to even intrinsically change the problem you are starting with. And because basically a main issue is that you don't know what is the number of edges on the shortest path. So basically just adding a constant is actually going to significantly disturb the problem. And actually, for instance, in the example we showed here, it's actually going to not going to be the same problem anymore here. So this is one issue that we notice for solving the shortest path problem. And maybe we want to think about what are some other phenomena that we are going to encounter if some of the edges, they have negative weights. So maybe there are some even a more weird case. So for instance, what if? So what if we have a negative cost cycle? So what do I mean by that? So for instance, maybe you can think about this case. So we have an S here, and actually we have three vertices here. So here maybe there's like a -6, and maybe there's like a -4, and this is like a 7 here. And whatever, maybe it's like a 1 here, and there's like a 1 to the t here. What is the shortest path from S to T here? So actually there is simply no shortest path. I mean, we just go like this. So there's like a 1 here. We just go this cycle again and again and again. I mean, each time we go this, I mean, it's like a -4, -4, -6, -4 plus 7, and the cost is -3. So if you want to consider like a shortest path, I mean, basically the path with the smallest weight, you just like do this cycle again and again. And actually, the shortest path you can achieve is actually minus infinity. So actually, we say that observation we are going to make here is that so basically, if some path from S to T contains a negative cycle, cost cycle, there does not exist a shortest ST path. I mean, otherwise we just looping the negative cycle. So this is the first observation that we can actually make here. So if there is actually like a path, ST path with a negative cycle, we just loop again and again. Actually, we are going to minus infinity, and this is definitely not some situation we want. But how about the other side? What if a graph you study has no negative cycles? Does that promise that you can actually have a shortest path? So the answer is actually yes. So basically, we are going to discuss about the other side. So if G has no negative cycles, then there is a shortest path from S to T. That is actually further have the fact that it is actually a simple graph, a simple path. By simple, it means it does not repeat nodes. And hence, maybe let me use this. And hence, has at most n-1 edges. So this is something that we want to show next, that as long as the graph does not have a negative cycle, so the shortest path problem is actually still well defined. Okay, so why this is the case? So suppose that the shortest path. I mean, we basically want to show that the shortest path is a simple path. So if the shortest path P from S to T repeated the vertex V. So basically, we could remove the portion of P between consecutive visits to V. That is basically saying that assume that you have an S here and you have a T here. So basically, I mean, if it is not a simple path, so basically, maybe you have like a path, for instance, here to V here, then basically, if you see this repeated, basically this then is basically like a path like this, and then you go to T here. Because we don't have any negative cycles here, you can just feel free to delete this, and actually the value of the ST path is actually only going to at least not decrease. So and actually resulting, we say that is resulting in a path of no greater cost than fewer edges. Therefore, without loss of generality, we can assume the shortest path from S to T does not repeat any vertex. And I guess it's just like two move methods like this. So any questions about these two observations? I guess basically the first observation is quite direct, as if you have a negative cycles, this is going to give you a severe problem. But actually, on the other hand, if all the cycles are at least non-negative, then basically all the shortest path should just be simple, because removing such kind of cycles, for instance, basically a cycle on V here actually does not going to influence at least you are actually going to get a path of no greater cost, and actually this is only going to give you a better, at least not bad, shortest path here. Okay, so basically, from these two observations, we can say that we can consider the following problem. So basically, we can consider like a harder shortest path problem that compared to what we have been discussing about compared to the Dijkstra's algorithm. So basically, we consider the following version. So the problem is that consider a directed graph. G equals to V and E here. And actually suppose that G has no negative cycles. And the goal here is to find a path T from an origin node S to destination node T with a minimum total weight. So this is basically going to be the improved version of the shortest path problem. So here we are talking about shortest path. I mean, to make the let the problem make sense, we basically need to assume that this graph has no negative cycles. But only having this assumption, I mean, in general, I mean, we can have a negative edges nevertheless. I mean, what is a good algorithm that can give a shortest path for this? Okay, so basically based on the discussions above, basically we can clearly see that we need fundamentally different ideas. And this is, for instance, we are going to do this by dynamic programming. Okay. So we have basically introduced the problem statement of the current shortest path problem. So let's think about, for instance, if we want to use the dynamic programming idea to solve the problem, what other parameters that we need to be careful about? So we basically want to have like a good usage of this assumption that G has no negative cycles. And basically, I think a key observation that we make is that basically we can assume, nevertheless, we can still assume the shortest path is a simple path. And basically the length of the path is at most n-1. So basically, something that is good that we can utilize is actually the length of the shortest path. So basically, it makes a lot of sense that we have one parameter to represent the length of the current path. And of course, the other parameter is going to be the vertices. So that basically comes to the idea. So it is basically on this, we can use OPT of I on V to denote the minimum cost of T path. So basically, I think basically for doing the OPT, I mean, I'm fixing one of the S. We should fix one of the S and T here. I guess without loss of generality, let's say we fix the T here. And basically the parameter in terms of V here is basically in terms of the starting vertex. And basically we want to characterize the OPT and basically the minimum cost of a VT path using at most I edges. So by our observation above, it suffices to compute the OPT of n-1 and S. Okay, so any question about the problem and the dynamic programming? So the next thing is, I mean, this is probably intuitive. I mean, let me improve some of the writing here. So I guess this is probably intuitive that we can maybe, for instance, we consider such kind of OPT function using a dynamic programming. But very importantly, what is the recursive relationship here, or we can say how to solve this by dynamic programming. So basically, to have a good understanding about what the recursive formula is, we still need to basically take a close look about the optimal solution here, about like the intrinsic structure that is actually going to have. So let's actually consider different options for building up such kind of path. So what options do we have here? I mean, we are talking about, I mean, recall that the OPT IV here is denoted as the minimum cost of a VT path using at most I edges. So of course, I mean, if the path P, I mean, it does not use all the I here. Basically, if it uses at most I minus 1 edges, then OPTIV is going to equal to OPTI minus 1V. So of course, I mean, there is another case that if the path P uses I edges. I mean, if it uses I edges, I mean, after all, we are going to have a first edge. I mean, let's say the first edge. Let's say like VW, then we basically know, I mean, after having walked one edge, I mean, the remaining part should only have at most I-1 edges. So we know that the OPT IV is in that case going to be the cost of CVW. The CVW is just the cost from V2W plus OPT I-1. So here you have been going, I mean, you have been going from V to W here, and maybe you have a lot of edges and TOT here. So of course, then the value of the OPT here should be OPT I-1 and W, because now you are going to talk about a path from W to T here. So therefore, I mean, we can clearly see about the relationship here. Therefore, basically, we obtain the following recursive formula. We're actually, if I is larger than 0, then basically, we know that OPTIV is actually going to be the minimum of OPTI minus 1V. And also on the other hand, mean of W belongs to V, OPTI minus 1W plus CVW. Then we call this is the star. So any questions about this observation for dynamic programming here? Okay, so this clearly gives us a dynamic programming algorithm, and this is typically called the Bellman-Ford algorithm. Bellman-Ford algorithm for the shortest path problem. So how does the algorithm look like? So let's just write Bellman-Ford. G, the graph, and the two vertices S and T here. So initially, so here, I mean, the OPT, I mean, we have two parameters. We have an I and we have a V here. So actually, it happens that both parameters, they have a size at most n here. So because the I here, I mean, we are talking about the simple paths. Simple path is going to have length at most n-1. So it is fine that we use a register of size n here. And also on the other hand, I mean, the V here, the number of vertices is also just V here. It's also just n here. So basically the other register, the size should also be n here. So just initially, we are going to have like a square matrix, n by n matrix. And basically, we are going to know that I'm 0, t is actually going to be 0 because actually, I mean, if you are already at t here, I mean, the shortest TT path with length 0 is, of course, this is going to give you value 0. And actually, we can say that M0V here is actually going to be a positive infinity for all other V belongs to V. Because it's just impossible if you have no edges and your other vertices, you cannot reach V here. So we just say initially all the other entries of the matrix initialize to be a positive infinity here. So the algorithm after that is actually quite intuitive. So actually for it is also a double loop. So let me write 2 for it here. So the first loop is actually going to be for I goes to 1, 2, until n-1, because we know a simple path is going to have length at most n-1. And the other 4 is actually going to through all the vertices V here. So basically, we are going to compute, I mean, in this recursion, we are going to compute OPTIV using the recurrence in star, the equation star here above. And actually, finally, we are going to return the entry of m minus 1, yes. Any question about the Bellman-Ford? Okay, so I guess the intuition is probably clear to you. I mean, that basically this Bellman-Ford algorithm is actually a correct algorithm. I mean, the idea of dynamic programming is actually quite clear here. So the remaining thing is that basically we need to give analysis about the cost of the Bellman-Ford algorithm. Basically, the cost of the Bellman-Ford algorithm actually are more expensive than the Dijkstra's algorithm. So basically, we introduce when we introduce Dijkstra's algorithm, we also introduce the heap data structure. And actually, for the cost of the Dijkstra's algorithm, let me recall Dijkstra's algorithm. Actually has a time complexity O of m log n. So basically, we use the heap data structure to maintain the running of the Dijkstra's algorithm. So here we are going to give a theorem for the Bellman-Ford algorithm. So the Bellman-Ford algorithm actually has we can always say that can be implemented in actually O of n times m plus n time. So this is what we are going to prove next. So why is this the case? So proof. So basically in the recursion. So the recursion star, let's actually, for our convenience, let's actually copy this here again. So actually OPTIV it actually equals to the mean of OPTI minus 1 V. And the mean of all the W in V of the OPTI minus 1 W plus CVW. Now basically we are calculating this. So what is the cost instead each of the for instance, because the first for loop, we are actually fixing an I here. And basically after fixing an I here, we are using this for loop. We go through all the vertices and we are going to update the corresponding OPT here. So one thing that we can observe is that for a fixed I, so basically the minimum is actually taking among, the degree, the odd degree of V plus 1 entries. Oh, I guess here, yes. So basically here, Y is like a degree plus V plus 1 entry. So this is the additional entry because it may actually work that OPTI minus 1 V is actually the smallest. Compared to all these means. Actually, the number of means that here, it is only meaningful for all the W's where actually we can reach W. Basically, we have such kind of an edge here. So the degree plus V is basically the odd degree of the V here. And basically, this is the size of the mean W in V here. And basically, we have another entry here. And that is the reason why we are saying that actually the minimum is actually taking among only a degree plus V plus 1 entries among this. So actually, let's actually see. Take a note here where degree plus B is actually the number of edges leaving the number of odd edges or odd degree here. And also on the other hand, note for a directed graph. Basically, each edge is an odd edge on one vertex and each edge on the other vertex. So basically, we know that the summation is actually going to be exactly n. because each edge is, as I just mentioned, is exactly one odd edge on one of the vertex. So therefore, each iteration, the total update cost is basically O of summation of V a degree plus V plus 1. Actually, this is exactly M plus N. And this just imply that the total cost of the Bellman-Ford algorithm. I mean, we definitely need to go through all the iterations from I equals to 1 to N minus 1. Is going to be O of N times M plus N. And actually, needless to say, this is probably in general more expensive than Digestras. Okay, so is there any question for this Bellman-Ford algorithm and this time cost? Yes. Sorry, you're talking about here or? Uh-huh. Yes, yes, for I from 1 to N minus 1. Yeah, this I is just like the current length, I mean the length of the shortest path with at most I edges. And because here we stop at N minus 1 because basically by the observations above, we know that, I mean, a shortest path, I mean, as long as your graph does not have a negative cycle, it should be a simple path, and a simple path should have at most N minus 1 edges. So basically that is why the OPT here, we actually stop at N minus 1 here. But actually to figure out what is the behavior of the algorithm, we actually need to go through all the I's. I mean, basically shortest path with at most one edge, two edges, three edges, etc. until N minus 1 edges. And basically that is the role of the I. Any other questions? Okay, so basically we can basically the conclusion, a brief conclusion we can get here is that basically for this shortest path problem, I mean, even if it has a negative weight, we can still solve the problem, and basically we can solve this by this Bellman-Ford algorithm. Although the cost, I mean, compared to Dijestra's algorithm that only works for negative weights, the cost, I mean, the time complexity is indeed larger than that of the Dijestra's algorithm. So there are basically like pros and cons between these two algorithms. So basically, I mean, we can talk about some further discussions along this problem of the shortest path. So in general, maybe a first question that you can in general imagine that, I mean, we've also discussed about this question, the sequence alignment problem, that what if we not only want a value, but actually the shortest path. So I think it is not that easy to improve the space complexity of this problem. So I guess like a brief answer to this is basically that we can do this. So basically, I mean, basically we see that we have this table of M here. So basically, we can basically add an additional register at each vertex, and we define. Basically, we define another array called first V for all V in V here. So basically, we update its value. We update its value whenever MV is updated. that is basically when the minimum of W in V on M W plus W is reset set first V to be the node W that attains the minimum. So basically, you can clearly see that the intuition is quite clear. I mean, as long as each time you actually update the corresponding value, then you basically update this value of the first V. So basically, as long as you have like an entry storing this first V here, you can just like trace back. I mean, you can just like trace forward, and basically you have the V, and you go to first V, and after you go to the first V, you go to the first of the first V, and basically you can figure out such kind of paths. So maybe one notation here is that I mean, here I'm only writing MW here. I mean, what does this mean? Because actually for the M here, actually it is an array of two entries. So this is actually another observation that we are actually going to make, especially about the space complexity. And actually the space complexity, I mean, it is not like a divide and conquer this kind of approach, but in general, I mean, this is actually a more a direct observation. So like a naive way of implementing Bellman-Ford. I mean, of course, this is going to take, you can finish the task in O(n) squared space because this matrix M is actually n by m square matrix. So O(n) squared space complexity is always going to work here. So for the following thing that we can actually do is that, in fact, a more clever way is that, I mean, the I here is actually more as like a counter instead of actually you really want to. I mean, I'm actually not asking you to figure out like the shortest path with like at most how many edges. So this is actually not required, though actually this is super convenient for us to figure out. I mean, we know that I is actually at most a -1 here. So this is actually super helpful for us. But actually, in fact, I mean, only speaking from the perspective of outputting the shortest path. I mean, I here actually acts more as a counter. And actually, the observation here is that we can store a single value MV here at each vertex V, and actually after that perform the following update. Basically, which is going to be just MV equals to the mean of MV and the mean of W in V. W plus CVW. So as I was discussing here, the I here actually acts more like a counter here. And actually, if we only if we're actually satisfactory to have like a shortest path, I mean, we know that the shortest path has most -1 edge. It suffices that we only actually maintain a one-dimensional array here with n entries. At each time, I mean, we just recursively, sorry, not recursively, but each time we just like iteratively update this. I mean, we just have the minimum of the MV here, do the minimum of MV, and also all the minimum of WV. I mean, at the current iteration, we need to be make a good synchronization here. It's just like at each iteration, we just update all the M's here, and basically we use all these value of M, we can update the next row here. Basically, somehow there's still like the sequence alignment problem because basically we have like each time we have a fixed I-1, and basically we can use the current value of the M's at the iteration I-1 to figure out that in the iteration of I here. But actually, we don't need to explicitly store that. Actually, we can actually reduce this with the cost. Basically, only using one-dimensional RAM here to do this kind of minimum. And actually, by doing this, we can say that therefore, Bellman-Ford can only take O(n) space. And actually also combined with the discussion above, we can further based on this observation, I mean, still we can actually use this to recover the shortest path by actually maintaining another array called the first. And actually, this is going to also give you another overhead of space complexity O of n, but nevertheless, I mean, On plus On is still O of n here. So in general, the space complexity for the Bellman-Ford algorithm, even if you want to recover the shortest path, is still O of n. Okay, so any questions here? Okay, so I have about 15 minutes, so I think that is probably just enough for the class today. So the very last topic that we are going to talk about today, and in general for dynamic programming, is basically negative cycles. Negative cycles in a graph. I mean, so here we basically we have been discussing about this shortest path problem a lot, and I think we can not very hard to see that by our observation above. Finding shortest path only works when the graph does not have negative cycles. I mean, for the Bellman-Ford algorithm, we are actually working under the promise that the graph does not have negative cycles, and basically this works. I mean, like a more general question, and in general, maybe we want to ask is that, for instance, on the other hand, can we actually detect negative cycles efficiently? I mean, by a detection is just like ask you to output a negative cycle if it exists. I mean, if it exists a negative cycle, we just don't need to run the Bellman-Ford algorithm anymore because the shortest path problem on a graph with negative cycle is not well defined. But nevertheless, if we make such detection and there is no negative cycles, and then we can go to the Bellman-Ford algorithm. So basically, I mean, this is still heavily based on analysis of the Bellman-Ford algorithm. So let's consider this. So we consider running the Bellman-Ford algorithm. For n iterations. I mean, for one more iterations, the Bellman-Ford algorithm only run for n minus one iterations. So we run Bellman-Ford for n iterations, and we mark this. N minus one iterations. So a key lemma that we can actually show here is that actually if OPT NV is smaller than OPT n minus one V for some node V, then any excuse any shortest path from V to T contains a cycle W. Furthermore, W has negative cost. Okay, so basically this is a very important signal. So if we compute the Bellman-Ford algorithm for one more iterations, so basically we have the value of OPT NV, and we make a comparison to OPT n minus one V here. So this is a very important sign that if OPT NV is smaller than OPT n minus one V here, basically we here at least we detect a cycle here, and if it is smaller, actually we can say that this W actually has negative cost. So we actually make a proof for this lemma. So basically, since OPT NV is smaller than OPT n minus one V, so due to basically the star. So the star is basically the recursion here for the Bellman-Ford algorithm, and actually quite intuitively for the dynamic programming idea here. So basically, due to the star here, we know that P has exactly n edges. I mean, because actually for the star here, we are taking the mean of the previous iteration and the mean of the others. I mean, we know that actually here it is strictly smaller. This is strictly smaller than this. So this just directly means that actually P has exactly n edges because we are discussing about this case. I mean, for the Bellman-Ford, and actually we've actually used at most -1 edges. Actually, the OPT must equal to the previous iteration. So we know that the current P has exactly n edges. And actually, if you have a path of n edges, and actually there are only at most n vertices, and basically each edge, I mean, going from one vertex to another different vertex. So basically, we can say by the pigeonhole principle, basically P must contain a cycle. So we now know that this P is actually having a cycle, and I think a clear thing that we can observe is that deleting W actually yields a VT path with smaller than n edges. But we know currently OPT NV is actually smaller, strictly smaller than OPT n minus 1V. And actually, this path, I mean, this path P deleting deleting W is actually, it must belongs to the cases where OPT n minus 1V has started. But actually, we know that OPT NV is actually smaller, strictly smaller than OPT n minus 1V. This just means that W has negative cost. Any question about this lemma? So on the other hand, we can actually, I mean, this is actually quite intuitive. I mean, if we run this Bellman-Ford algorithm for one more iterations, and we notice the OPT value is actually smaller than the previous iteration, then we know that actually this graph must have a negative cycle. So actually, on the other hand, if OPT and V equals to OPT and minus 1V for all V, then there is no negative cycle. So I guess this should be relatively straightforward. I mean, let me just briefly saying that the proof is actually similar by a contradiction argument. I mean, that just means if there is a negative cycle, we cannot have OPT and V equals to OPT and minus 1V for any V. This simply cannot be true. It's just like find a path. We're actually going through the cycle with length n here. So actually, I guess this is clear that actually this is not going to work. So basically, I mean, from these two lemmas, we clearly see that we have like a exact criteria of determining whether a graph has a negative cycle or not. I mean, this is just going to give us a very direct theorem, saying that actually there is an algorithm that can output a negative cycle if it exists, or output English words no negative cycle in O of n m plus n time and O(n) space. So I guess this is actually quite intuitive, and actually let's just give the algorithm here. The analysis is actually all the same to the Bellman-Ford algorithm. So here actually we are doing something slightly stronger. So here we are saying that we want to output a negative cycle if it exists. So here we want to be slightly more careful here. So we see such kind of algorithm. So basically we add a new node T, and actually connect our nodes to T with zero cost edge. And actually, we run a Bellman for very importantly, n iterations. So after that, we are going to check if OPT and V equals to OPT n minus 1 V for all nodes V. If yes, and then basically we output no negative cycle. And if no, then what is the advantage of having this T here? And in general, I mean, basically, this is actually for our convenience of putting this negative cycle if it exists. And if in this no case, it does exist. And then basically what we do is that we extract the cycle from the shortest path from V to T. So let's finally draw a graph, I mean, for this. So let's, for instance, consider this graph. So here, let's assume that there is an edge of length 5, of weight minus 5, weight minus 6, and 2, 6, plus 10. So let's just think about what will happen after we run this algorithm. So actually for this algorithm, we do have a negative cycle. So basically this is a negative cycle. So the reason of having this specific T here is that, for instance, assume that we draw a T here. Let me actually use the blue color here. So assume that we draw a T here. So we are actually having edges all having zero cost to T. So basically, I mean, if you run a Bellman-Ford algorithm, you will actually notice that such kind of V, I mean, this vertex and this vertex, they can also be the V here. But for instance, for this V, you will notice that actually OPT n V is actually smaller than OPT n minus 1 V here. So actually, we know that for the Bellman-Ford algorithm, especially for the space complexity implementation, we can have this first, we basically, I mean, after having this figure out the shortest path, we can store this first V, another array, to actually figure out what the shortest path is. I mean, basically for this, I mean, after doing this kind of iterations, you will actually, I mean, you will notice that for this vertex V here, the OPT value, OPT NV, in this smaller OPT n minus 1 V here. And basically you use the previous information, you just recover what is the shortest path. I mean, you just do this and actually, you just call this first V, you will figure out what this is. And actually, this basically ends the problem here. Well, I think I should draw this V here. Okay, so basically this finishes the discussion of the shortest path problem and also the how we can actually detect negative cycles in a graph, both actually by the Bellman-Ford algorithm. And though there are actually a little bit technical details that for a Bellman-Ford algorithm, we can actually implement this in actually ON space, and actually we can recover the shortest path, and also by running the Bellman-Ford algorithm for n-1 iterations and n iterations respectively, we can actually use this to detect whether the graph is actually having a negative cycle. Okay, so any questions in general about this topic?
But we really talk about the Floyd average, which is also
No, I'm not talking about that. So what problem is that for?
for the mounting source and mounting destination.
Right. No, I'm not going to talk about that because I think, especially I think this is a graduate course. I think the target of this class is not to talk about everything in fully detail, but to cover different aspects. So basically for the next class, I'm going to talk about network flow algorithm. So I think especially I'm trying to find some showcases where it's going to, in general, demonstrate some ideas of arithmetic ideas. And maybe, for instance, when I'm talking about some greedy algorithm or dynamic program, it's not something you're familiar with. I mean, especially the previous case used dynamic programming ideas. But hopefully, I think in general, this gives you some helpful perspectives. Okay, so since we're running out of time, so this is the class this time, and for the next class, and maybe next 1 or 2 class, I'm going to talk about the next network flow algorithm, its corresponding applications. Thank you for your attendance.